Okay, welcome back to the QuadTree project. Over the last couple of videos, what we've done is build a QuadTree structure which holds point data. So each of the point has an X and Y position associated with it. And the QuadTree subdivides if there's more number of points in a given QuadTree node compared to its capacity. So just to see what this looks like, let me just quickly compile and render. And you can see that we have our basic QuadTree data structure here. And if I click, it adds a new point. The capacity of the QuadTree is 5, so if I add one more point, it subdivides, and it continues to subdivide when each of the subdivided node has more than 5 points in it, like so. The issue with this is that as we add more and more points, the performance is actually very sluggish. As you can see here, as I'm continuing to click around, but the QuadTree is very sluggish in order to actually render those points. So today I thought we could take some time to actually try to optimize our QuadTree rendering and see exactly what the issues are. So to be consistent, what I want to do initially is to actually randomly add 100 points or 50 points or something, so that we're not clicking each time we want to render this. So to do that, let's import the random library and use that to initialize 100 random particles or 50 random particles. So C++ random is kind of strange. What we need to do is to actually define a random device and then a random generator. So let's do both of those first. So to do the random device, what we're going to do is just create a random device. And this is not random in the sense of like it's any device. It's a device that creates random numbers. So random device like so. And then we're going to create a generator, and there's different options for generator, but usually the easiest one is something like this. Without going into too much technicalities, it's just an algorithm that generates random numbers. So this is our generator, and it's going to take in this random device that we have over here, like so. And so now that we have our algorithm for generating random numbers, what we need is an actual distribution. So let's create a uniform real distribution, which is going to give us a double as an output. And this is going to be our distribution where we pass in the minimum and the maximum, the lower bound and the upper bound of this distribution. In this case, we want to define point values, so it's going to take 0 to 25, which, as you can see down here, is our the bounds of our domain. So now that we have our distribution, which is going to return a value between 0 to 25 with a uniform distribution, let's essentially loop through maybe 50 points and add them one by one. So let's create our X and Y position. So our X is just going to be our distribution, and this is going to take in the generator that we defined earlier. And then we also want our Y value, and our points is going to be stored in a vector of shared pointers. So let's create our new shared pointer. So std shared pointer of type point is going to be we're going to create a shared pointer of type point, which takes in our new X and Y point. I can spell that, yes. So we're going to create a new point, and we're going to insert this into our points vector. And we're also going to insert it into our QuadTree, like so. And now if I recompile this, I should hopefully not have any issues. Yep, I don't have any issues. And you see that it's created 100 or 50 random points throughout our domain. Like so, if I run it again, you can see it's generating a different set of 50. So every time I run this, it's creating a new set of 50 points that's uniformly distributed throughout the domain. Okay, so now that we have our 50 points, let's see what how long it's actually taking to render these 50 points. To do that, let's use the chrono library. The chrono library is what we use for measuring elapsed time in our program. And what we're going to do is to create we know that we're not actually calling this too many times. So the computation is not actually being held up by our point insertion because we're inserting our points at the start. So what we'll do is to figure out how long it takes to run these two functions, because this is where our draw calls are actually happening. So to do that, let's create our start and end times, and this is just a chrono, and I think this is steady clock now. like so. And then our end, which is chrono steady clock. No, so we have our start and end time, like so. And what we need to get the duration in double. Duration is going to be taking our chrono and cast the duration to a duration unit. So in this case, let's convert it to milliseconds, like so. And this is going to be the input here is going to be our end minus start. So there's an issue here because this duration cast actually produces a duration structure. So what we need to do at the end is just have a count, and this converts it to our double. So what this does is take our difference between the end minus start, convert it to milliseconds, and then we're actually getting out the value by doing a dot count. So let's print this out to screen. Frame took, we can do 2 decimal places, and this is going to be our duration. Excellent. And when I run this, you can see that the frame time is about 50 milliseconds. So each frame is taking about 50 milliseconds to run. This is outside of when we're trying to add any new points in here. And you can see as we add more and more points, it's actually taking longer. So there's something with rendering these large number of particles in our QuadTree structure. To figure out exactly where this is happening, let me move this around. So let me see if this is happening with just the points. So right now we're only seeing how long it takes to run these 3 lines. And you can see that rendering the points is actually not taking any time at all. Even if I add a bunch of new points, it's still taking on the order of 1 millisecond. So our main load is coming from the QuadTree, rendering of the QuadTree. Like so. Just to see how long this takes. You can see that rendering the QuadTree, which is these 2 points over here. So this line over here is the one that's actually taking the longest time. And this kind of makes sense because if you look at our render points function, you see that we're actually creating a vector of vertices. And once we have all of these vertices, we're actually doing a single draw call to render all of them as points. For the QuadTree, we're actually rendering individual QuadTrees at once. So the more nodes that you have, the more draw calls that you're actually doing. And the draw call is being set here. And so the biggest issue with SFML is the more draw calls you have, the longer it's going to take. And so ideally, you want to actually take all of your draw calls into one. So you want to essentially cache all of these operations and then draw them once rather than drawing multiple rectangles at a time. So let's fix that. So let's keep this as it is, and let's try to figure out how to fix this. And the best way to do that is very similar to what we have here. So in render points, what we're doing is collecting all of our vertices, all of our points, and then rendering them as individual points, like so. For the QuadTree, we're actually creating multiple rectangles, and then we're drawing them all at once. Which is very, very expensive and very costly. So we should use something like this, where we're collecting all of our rectangle data and then generating them as lines, essentially. So if you look at the documentation for SFML, here, let's see, it should be the vertex. If you see how vertices are defined, vertex array. I think it might be actually primitive type. Yeah, there you go. So what we want is we rendered all of our points as individual points. We could render all of our QuadTree structure as line strips. So list of connected lines, a point uses the previous point to form a line. So another option might be to actually render them as individual lines. So what this does is every double set of points will be treated as a single line. So you add 2 points at a time, and this will be rendered as a single line in your data set. So you could use either of these. We could see how it works. The benefit of something like line strip is we only have to define one point each time. And so we could render individual nodes of the quad tree at once. The benefit of the lines is that we can render the entire quad tree if we're able to accumulate all of the points across all of the different nodes in that quad tree. So let's try out the easier version. Let's try out the line strip first. And if this gives us the performance benefit, we can stop there. But if we need more performance, then we need to do this. Remember that the difference between the two is the number of draw calls that we're making. Here we're still going to be making a single draw call per node, which is very similar to what we already have. So this is doing a single draw call per node. The benefit of this is that we only do a single draw call per frame. So this is definitely going to be a lot easier, or a lot more efficient and more performant. But we can try this first, and if it doesn't work, we should be able to do this. So let's start with that. So what we want to do is to essentially collect the 4 corners of our quadrant, of our node, and then render them very similarly to how we do this. So we want essentially the same data structure for our rendered quad tree function. So let's do that. Let's create we know that this is going to be std array of SF vertex. And we know that's going to be only 4 of them, 5 of them, because we want the each of the 4 points, and then we want to repeat the last point so that it loops in on itself. And this is going to be our lines, like so. So what we're going to do is to lines 1, we need to set the lower left. Lines of 1 is going to be set the upper left. So lines 2 is going to be set the upper right. And then lines 3 is going to be set the lower right. And then the last point is going to be the lower left again, like so. And we don't need this. And we just want to, let's just copy this over. So instead of vertices, we want lines, like so. So let's actually set this. So what we want here is we want to transform to world space. Do we want to? No, we want to transform to pixel space. We want to transform to pixel space, and this is going to be the lower left location of the point. So this is going to be qt.bounds.xmin, and then qt.bounds.y. We already have the bounds defined, so we don't actually need to. So okay, and now we just repeat the same thing. So transform to pixel space. In this case, we want the upper left, so this is going to be bounds.xmin and then bounds.ymax. And then this is going to be upper right is going to be bounds.xmax and then bounds.ymax. So and then this is going to be lower right, so bounds.xmax and then bounds.ymin, and then we're just going to repeat the same thing over again. Let's just type it up. This is going to be xmin and then ymin again, like so. And so now that we have our lines data, we don't want to render this as points. We want to render this as line strip. So play this out. Let's see if this works and see if our performance has improved somewhat. So we went from about 50 milliseconds to about 30 milliseconds. Let's try that again just to see if that was a result of the randomness. It doesn't seem to be. We seem to have consistently dropped about 30 frames, but this is still pretty slow. And it increases with the number of quad trees that we're rendering because we're adding multiple draw calls per quad tree. Yeah, so we're hovering between the 30 to 40 milliseconds, which is pretty slow when you look at the fact that we're adding only about 100 points or so, or not even, we're adding only about 50 points or so. And the benefit of the quad tree is really from having thousands of or tens of thousands of points. So if we're seeing performance drop at the 50 points level, then we're not actually leveraging any benefit from our quad tree when we're doing any sort of visualization. So the line strip method is actually pretty slow. So what we really need to do is to switch over to a lines method instead. So let me just put that up. I'll pull that up again. And so essentially we want to switch over from the line strip method, which is what we're currently using, to a lines method, where we have basically the same same ideology, where we're creating a vector like so. We're creating a vector of points or an array of points like so. It should be a vector because we're accumulating pairs of points. And for every pair, it's going to draw a line. So let me just render the exact same thing as a line, and you'll see what the difference is. So you see, I'm rendering this as a line, and what's happening is that it's generating the very first line between the first point and the second point, and then it's generating the next two set of points, which is 2 and 3. So that is we're going from the lower left here. We're going from the lower left to the upper left, and then from the upper right to the lower right. And that's exactly what you're seeing here. Lower left to upper left, and then upper right to lower right. And it's completely skipping the point in between. We can fix this by adding more points. So we can fix this by saying, well, what we actually want to do is we want the upper left again. So from upper left, we want to draw upper right, and then we want from upper right to lower right. Let's just increment these like so. So we want upper right to lower right, and then lower right back to lower left, like so. And so now instead of 5 points, we actually need 7 points. And if we do this, we're actually getting our original quad tree structure back. And that's because for every point, I think I made a mistake. Missing a couple of points. So lower right, upper right. Let me just see if I did this right. So from lower left to upper left to upper right to lower right to lower left. This should be correct. I see. I've incremented this incorrectly. 6 and 7. We actually need 8 points. Yeah, that makes sense. We need, for 4 pairs of points, we need 8 points. There you go. Now we have our quad tree structure. It's still taking the same amount of time, essentially. But what we can do is to accumulate these pairs of points globally into a global vector of lines, and then render the line at the very end. So let's do that. There's a hacky way of doing this, and then there is a clean way of doing this. As is always the case, let's do the hacky way first, and then let's do the clean way later on. So what we want to do is let's create a global lines variable. So std vector, and this is going to be an sf vertex, and this is going to be our quad tree lines, like so. This should be an extern, like so that we can define it up here. Vector, and this is going to be sf vertex. And this is going to be a quad tree lines, like so. That's correct. And what we want to do is, instead of lines, we want... Okay, we should fix this, but let's come back to it in just a second. Now, there's an important caveat here that the way of doing this right now, the way that we've done it by defining a global vector and then accumulating the list of points, it's an atomic operation. So you cannot actually do this with multi-threaded applications if your different parts of your QuadTree are being handled by different threads, because they're both going to try and accumulate to the same QuadTree, same vector over here. This only works because our application is single-threaded, which is why it's the hacky version, and we don't care about multi-threading or multi-core performance or anything. That sort of optimization is going to be completely beyond what we're doing here. So, but that's just an important caveat here. The way we're doing it is making the assumption that whatever we're doing is going to be handled by a single thread and a single core. So we need to fix this in just a second. But what we want to do, the algorithm here, is that we have our global list of lines, and every time we call this function, every time we call render QuadTree, right? Remember, we're passing in the level 0, the initial QuadTree structure, which has leaf nodes, 4 leaf nodes each, which each have their own leaf nodes and so on and so forth. So what we want to do is, as soon as we're past this function, we don't know if we're actually calling this from, remember this is a recursive function, so for each of the leaf nodes, it's actually calling the same function back. So what we want to do is to actually figure out, when we call the function for the first time, we want to make sure we do not have any accumulated QuadTree lines, any points. We want to clear it out. And at the very end, once we know we've accumulated all of the points, we want to render this out. There's multiple ways of doing this. We can split this function into two. We can say accumulate points, and then we can call it render QuadTree function. But let's try to do it all together. Because we know that if the QT, the QuadTree's level is 0, we can actually clear out the QuadTree lines. We can actually delete it out. And in the same way, down here, if the level, QuadTree level is 0, we can actually draw the lines. These should be QuadTree. I thought so. Okay. Let's just add this QuadTree lines. There we go. So basically what this is saying is, if we know that the QuadTree that we're passing in is the main QuadTree, then we want to clear out the lines so we can actually accumulate all of the points, do the recursive operation, and then once you recurse, this is never called because we know that it's not level 0, it's going to be level 1, so on and so forth. And at the end, once we've actually accumulated all of the points for all of the subdivided leaf nodes, we can actually render everything to screen. So the only thing we need to do now is to replace all of these these functions with a pushback operation. So let's do that. I'm gonna try and be. This is going to be a number. Let's see. And then we want to replace this with a pushback operation, like so. And then after the end of each of these, we want to close. Let's see if we can do it all at once again. We just want to replace our colon with that. Great. And these are not QuadTree lines. These are not lines. These should be QuadTree lines, like so. And that should work. Just making sure this is handled correctly. Yep. Okay. So instead of calling, instead of adding it to a defined index, what we're doing is just we're pushing back pairs of points. Let's just separate the two pairs just so that we know how it works. So each of these is the pairs of points, and they will be rendered as a single line from starting from this point to this point. And since we're accumulating this globally, what we're doing is essentially accumulating two pairs of points each time. I'm sorry, 4 pairs of points each time for every QuadTree. And at the end, once we've accumulated all of the points, it's just going to render that to screen. So let's see if this works. Let's see if we've made a mistake. Nothing seems to be crashing. And now if I run the QuadTree, you can see that the entire QuadTree structure is taking 1 millisecond to run. Because we've accumulated all of our points and we're doing the draw call once per frame rather than doing multiple times per frame or once per QuadTree structure. So let's be crazy here. Let's try to increase our points to maybe 5,000 or something like that. Yeah, let's do that. And you can see that with 5,000 points, with this many subdivided quad trees, it's still taking on the order of 3 seconds per iteration. So our even adding new points is actually really, really fast. So our quad tree structure is now very, very efficient, and it's able to handle a huge number of subdivisions. Cool. Okay, with these optimizations in, I think this is going to be the end of this episode. In the next one, we're going to start looking at how to actually start doing point-to-point interaction now that we know that our quad tree is well optimized and our rendering is also really well optimized. So that's going to be a deep dive into how we want to move the points around and how we want to update the quad tree structure and how we want to query from the quad tree when we want to search for nearest neighbors and things like that. All right, see you in the next one.